what will happen in linker script, or from where stack initialize, or like that kind of things, from memory initialization and all these things?
Yeah, so my idea is basically to take you from zero today and show you sort of the whole process of just putting together all the files that's necessary to get an STM32 up and running.
Okay, yeah, sounds good. Thanks.
Yeah. Does that sound good for everyone?
Yeah, of course. Actually, one thing, Martin, like every time we are facing, so depends on the industry, we'll be working on different things, right? So, but most of the things are related to application level. So that's why even when we are working, we didn't get enough chance to get into driver level. For example, like, okay, how we can write the drivers and how we can what do you say, create the or programs like I mean driving programs for the peripherals. So these things are already embedded in many of the devices. Even when we are purchasing, we will be getting all those inbuilt. But knowing the science and what is the maths behind that is really good. Like, because every time working in the application, like no, I mean the top of the application, like for example, C code or CPP. So it won't, I mean, it is not giving complete understanding. So that is where I am lack of. Like every time, yeah, I want to get to know from the scratch.
Yeah. So one of my goals today is to make you never want to write this code yourself. Because you do get all of it with RTOS or with a ready-made system. Like when you start coding on top of RTOS, you don't really even see this stuff. So you start with just a one-liner to compile your application, and then you're ready to go. But then you're missing everything that's sort of happening underneath, and people are curious about what is actually going on. Like, how do you actually take a few simple C files and build an application for STM32? That will actually boot and start. So that's what we're going to be going over today. And by the time I'm done, I'm sure you will never want to write this stuff yourself.
Yeah, sure. Why STM32? I mean, in particular?
People are asking about STM32, and nobody asked me about anything else.
Okay.
I don't know why. Maybe STM32 is the most popular one.
Popular. Okay, nice. I also use STM32, but I just curious.
Yeah, and moreover, like there are so many different platforms and different courses are available through STM32, and most of the people nowadays, like even in magazines and everywhere, they are using STM32 for building different applications. So that's why people are going now.
STM32.
So are there any people on the call here who are using other processors? Tell me about it.
I mean, Cortex-M, I use it. So STM32 M0 to M4, this Cortex-M series, I have used it. So that I use.
So actually, what I did was like, instead of going for Cortex M4 or Cortex, what do you say, like more process of Cortex. So what I did was like, I started with Cortex M0. So which is like LPC11C or from NXP. So then I moved on. Why? Because writing the applications for the smaller processor, like which is having what do you say, less number of registers, and I mean less number of applications is really good. Like we will come to know the entire architecture initially. Then if we go further, like it will be good. So that's why I had started with this LPC11 C from NXP, that is Cortex M0 Plus. So I mean, apart from that, I do work on like MSP 430 from Texas Instruments, and TM14143C, that is also from Texas Instruments. So these are all, I mean, low power device, I mean, low power process. So where we can build like not many applications, but few applications on them.
Right. And is that mostly IoT applications you're building using those?
Yeah, that is true.
All right, cool. So one interesting project that I think everybody should know about is the Zephyr RTOS that is being developed under Linux Foundation. That is the fastest way for you to get an application running on top of a scheduler, on top of an RTOS, on many different chips. So it has support for lots of different controllers. and I really recommend everyone to check it out because that's working on a higher level, right? It's much higher level than what we're going to be doing today. So let's get started. What I'm going to do is basically I will share the screen on my other desktop, and then I'll continue there. So I'll be back in about a minute or so.
Yeah.
Pranit, do you work as a like?
Yeah, I have.
Full
Yeah,
time
I
or
have
student?
been.
Or, okay.
No, I have been working, and I mean from last 3 years.
Oh, okay, nice.
Yeah. And what about you?
Yeah, I'm also working. I mean, but I started just recently, like 10 months, like embedded software developer. Yeah.
Mm-hmm. Okay, so my area was like initially I worked on hardware for around 1 to 1.5 years, like FMEA, failure mode error analysis, and what to say, like schematic designing and everything.
So
So,
PCB
but
designing and like that thing.
no, it's not PCB design. No, it is most of the circuit design, because whatever the netlist that we will be giving through the circuit design, that will be given to PCB people so that they can build the PCBs.
Okay.
Yeah. So, but in my company, we did have more scope to evolve in like hardware designing. So, I mean, we lost the project, so I could not get any other things. They asked me to move to complete software, something like a .NET and everything. So I don't want to go for that. I stayed in this firmware. So I shifted my domain to firmware.
Yeah, that's nice.
Yeah.
So now the project you do it with this thing, NXP,
It is
and
no,
which
actually.
controller or which processor do you use? From which company?
Actually, that was learning for me. Like whatever
Okay.
I said is that is I'm learning. But apart from that, I am working for oil and gas industry, which is IIoT, Industrial Information, the Internet of Things.
Oh, okay, nice.
Yeah.
Link is not yet started.
So, hi Patrick, can you hear me?
Yes, of course. Very good.
Yeah. So, where you're from and which domain you are working?
Actually, I am from Poland, and I'm working as you were working as a hardware engineer.
Yeah.
So you mentioned something about FMEA analysis.
Yes,
so
yes.
Actually, I really know what this means, and it's actually pain in the ass. I would it's something like this. And right now I'm working also as a hardware engineer, but for different company and different industry. Previously, it was for automotive. So I would say that automotive is area what I want to avoid in future. And yeah.
Many people were saying, actually,
Why?
some of my friends are traveled to Poland. They studied there in Warsaw, and they are also working same in automotive industry. So everybody is saying that after working there for some time, they want to switch to other domain. They don't want to be in automotive.
Why? Can I ask?
Yeah, actually, the problem is with the volume. You have millions of pieces, and actually, if you want to change one transistor and the price is more than 1 cent or something like this, they will kill you in the best case. So if you have good ideas, you are not able to take this into schematic and after this into layout. It's actually impossible because of volume. So
yes,
different industries like IoT or connectivity is, I would say, better because you don't have that much pieces of hardware, and you may use another resistor, another transistor, and so on and so forth. So actually, automotive is good for figure it out how something work. If you have lower RDS on, how actually this impact your switching, what resistor you should use, something like this. But normally, when someone creating schematic, he would actually pick transistor with better performance for a little bit more than actually making some analysis or something like this.
That is true.
I mean, you both are like strong in hardware background, I guess, right?
I wouldn't say that it's kind
Yeah,
of
it's strong,
strong
but I do know the things. That's it.
More in
Bits and
hardware.
pieces
I
I do
mean,
know.
I don't hardware level. I mean, now I think what issues are in STM32
Yeah.
microcontroller. Their ID you get is STM32 cube ID. You might be knowing, and then
Yeah,
you
actually,
enable pins, you enable peripherals, what you want, UART, ADC, SPI, and then the basic code is generated. And based on this code, and if you want free RTOS, you order it, and then building the logic. So more in software domain. Building the functionalities and all this thing. I also did one project with 2G GSM connectivity and then controlling lights over the cloud. Actually, telecom cloud I have used it, but it's
Okay.
slightly more software into this thing. I mean, I'm in Germany here, so it's,
Okay.
Okay, guys,
I
I
can.
love the discussion. I think
yeah.
it's
Sorry.
it's a lot
Okay.
of
Okay.
fun just listening to it, and it's so much information being shared.
Yeah.
But we need to
Yeah.
get started.
Yeah.
So
Sure.
Yeah.
let's
Yeah.
get
This is.
started.
Yeah, that is true.
So I'm gonna start from the beginning. So we're gonna create a very simple application that just starts and loads into the processor. We're gonna flash it to an STM32 F429 board, and we're gonna run it. But normally you would get all of this stuff generated for you from an IDE. So you never really see those things that need to happen in order to compile an application with a tool chain and to make sure that you get a binary that you can flash and run on the STM32. So I'm going to explain to you step by step exactly everything that happens from the start when the application starts in the microcontroller and until it gets to main. We have, during the time today, I think we're not going to have enough time to really even get into any kind of peripheral configurations. We would have to do that on a different workshop. But we're going to get to main until we get to a while loop that just runs and loops forever. There is a lot more that's going on underneath. So I'm going to start with main. I'm going to just sort of get this application into a new folder, and we're going to start developing the application there. So we want to get this code running in STM32. What do we need? Well, we're going to need to link our program into a binary that can run on an STM32. And how do we figure out what this binary needs to look like? Well, there is a memory map in STM32. I think it's somewhere here. Let's see, memory, flash memory map that tells us the addresses of our memory. So we have our flash memory at 0800 0000, and this is where our code will reside. Can everybody see my screen, by the way? If my screen freezes, let me know, right? Then we have our RAM memory. It's at 0200. This is a smaller RAM memory, and then there is a main RAM memory. So this is the CCM, which is a core coupled memory, and this is the main SRAM memory, which is located at 2000. So this is where our variables will go. So when our application loads, from the binary, we're going to have to copy our data, that is initialized data, the initialization values of the data. We're going to have to copy that to RAM, to where our actual variables are, which our code will unchange. And then we need to start the code, it's gonna load. So the processor is gonna load the stack pointer and the address of the reset handler, which is going to be the entry point of the application. It's going to load it from 0800 0000. So the first word at this address has to be the pointer to the stack, to the stack of the application, and the second word is going to be the address for the program counter that's going to get loaded, and then the processor starts. So how do we achieve this layout? Well, to achieve this layout of the binary, we use what is called linker scripts. And a linker script basically looks like this. And this is a linker script for, this is a default linker script for STM32 F429 ZET6, which we're using. And we're basically gonna go over the script line by line, and we're gonna create a new file here. So we have our main, which is our program. Now we need to build this main into binary. So we're gonna do a linker LD, and we're gonna define our entry point. And this linker script is basically telling the linker. So once you have compiled your C code into object code, then you link that code with libraries and produce a final binary. The linker script tells the linker where to place all the code. And so the functions, the addresses, they get resolved at linking stage. So linking stage basically means that you are linking the addresses of functions to whatever references to those functions are being used elsewhere. So you can have a large project with many files where files can reference each other and reference functions in other files. And what the linker does is it basically translates or calculates those final addresses that are going to be used when the code is actually running on the chip. And it does so, part of the process of calculating those addresses is actually using those values provided for where the code is actually located in memory. So if we say that our code is located at 0800-0000, then when it's linked into an actual binary, the offsets and the addresses will be based at 0800-0000. And the linker uses the linker script kind of as a way of defining the layout of the final executable. So we're going to define our reset handler. Now, is reset handler a keyword? Well, no, it isn't. Reset handler, Nagarian, can you please, are you sharing your screen?
Me? Who? I cannot see it now.
Yeah, I know. Let's see.
Me too. I also don't see anything.
Something happened.
Let's see. Something weird happened. Let's see.
Small issue.
Yeah, I don't see anything either. That's weird. Just do this. So I don't get any kind of toolbar either.
No, maybe hanged. Your PC got hanged. Or?
No, I have the other screen working. It's just this screen.
Sometimes there would be the problem with the Zoom also.
Yeah. Sometimes Zoom has a problem of not updating the screen. So you think that you're showing something to somebody, like you're showing a presentation, and they're like you're telling them things, and they are saying okay, and then like 20 minutes in, you find out that they haven't actually been seeing the screen.
It was very interesting you are telling, and this is unfortunate.
Let's see. So I'm gonna restart this Zoom session and see if we can get back on track.
Yeah.
Then we should have to again click and log in. I mean, join it again.
No. I'm gonna join again.
Okay, sure, nice.
So I'm just gonna do like this.
Oh, this is nice. What you taught.
Yeah. So actually, yeah, we can talk something related to this.
Yeah. I mean, I never created this thing. I know from reset handler to the main we come, there is like different things happen from reset handler to main. And exactly that's what I was looking for. I'm lucky that, glad this session I found it and something I can learn today. So have you did anyone before this thing?
Even actually, even I am also not so clear. Like even I have to go through this because I do know that how the linker section is working and how we will be segregating the code memory, data memory, and other things. But how we link all these things to the main code, I also don't know. So if you
I mean,
know, you
that
can
is, I
explain.
think it is a command they do it. I mean, the from reset handler entry point and what you said, the memory difference. So below is the text segment. Every code come there. What we write it like converted
Yeah.
into the program. Then initialize all global and static variable. I mean, in all RAM, what is happen? I'm saying. After that, uninitialize section like BSS, it's called, where all uninitialized global and static variable get there. After that, then start the heap section from, so then maybe what Martin said, like from 2000, like 0x200, that is like from where the actual memory starts, heap memory and heap and stack memory started from that.
Martin is here.
Yo, it's good, nice.
Good discussion.
Good, no? Yeah, I think we learned this nice platform. Yeah.
Awesome. All right. So let's continue then. Yeah, so in the linker script, we're going to be basically defining those sections so that we can place the code there. And the reset handler is going to be a symbol that will be defined in code, so in assembly code, actually. And this symbol is then specified inside the linker script as the entry point. So normally, like for example, by default, you might have an entry point called start, which is something you have on like desktop applications. And that goes into libc sort of basic startup code that is linked into every single desktop application that you compile. But in our application, we use reset handler because it's also the address where the processor will restart when it is being reset, right? So first of all, we're going to define memory. And we have our flash. It has read and execute permissions. It's basically telling the linker scripts that we have a read and execute section. It is based on origin of 0x and then 0800 000. And its length is actually, in this case, let's see, we can actually do like this. The 16, I think this is one megabyte. And then next we have our RAM, which is executable read-write. You can actually run code from RAM in STM32. It's possible to load an application into RAM, like a smaller application. So you have your main application, you have your smaller application. You can actually run it from RAM. And this one is based at origin 0x 2000 0000, and its length of 120K. And then we have our let's see, SRAM 2. We can actually do like this. Check this.
Martin, can you please make the text of editor a bit bigger?
Yeah.
Thank you.
Let's see, can I zoom this in? That used to work. I can do like this. You can see it now?
Yes.
Awesome.
Thank you.
Okay, so I just want to clarify this a little bit based on the table so that we get exactly the same values in here. And it looks to me like we could actually do like this. So we have C. So the interesting thing is that the default values from the default linker script actually work, but it seems that they're not exactly the same. Let's see. Maybe I should actually open up the right datasheet. Because this is for 405. It's the same for 429. It's just different sizes of the memories. So I'm gonna look it up. Let's see. STM32 429.
I mean, how did you know it's not working? I mean, did you run it or like how?
Yeah. This one I've run it. I've run this application that I prepared. It's just that when I'm now doing it for you guys from zero, then let's see.
No, I mean that's all right.
So the application works. It's just that I had the wrong data sheet up, so the values weren't matching up, and I was like, why are the values different? And then I realized that it was a different data sheet that I had up in the browser.
F1429, yeah.
Let's see, I'm gonna go here.
There was no RM reference manual. RM.
Yeah, I know, but I wasn't able to click on it first. Now I can click on it.
Okay.
I think there was some script running on the side that was just slowing things down. There we go. Now let's see if we can find this 800. So we have to look at 429. So here we go. Yeah. So this matches up with this other.
So flash 80.
Yeah, this matches up with my example. That's good. So we have our flash, we have our RAM, and we have also then our RAM number 2, and that goes 1C, 1F, FF. What would that be? Yeah. And then we have those other memories, which we're not going to be using anyway. and we're not going to be using the DRAM either. So we don't need that.
Martin.
So this script contains a few other lines, which are used. For example, the SDRAM line is used when you have when you enable the FMC controller on the chip, and you access a parallel RAM chip alongside of your internal RAM. Then you can actually map that RAM in the linker script so that you can place variables there. And so when you are then loading your executable, you can actually have symbols that are located in the external RAM, and you can access those symbols like a normal memory, but they're connected to the chip externally. But we are not going to be using that. Then we need to calculate, so the next step in our linker script, we need to calculate where our stack pointer will be. And we place our stack pointer at the end of the main memory so that it grows downwards. So the stack pointer will be used every time you have a variable that is local inside a function. So when you call a function, the processor will push the return address on the stack, and it will decrement the stack pointer so that it points down in memory. And then any local variables that are accessed inside the function, they will be automatically reserved on the stack. So when you have local variables in a function, your stack pointer will be decremented by the number of bytes that are necessary to contain those variables. And then when your function returns, the stack pointer will be set back to the, so the return address will be read, and then the processor will go back to the previous function, and the previous function will start filling the stack from the position where it was when it called your subroutine. But when we are starting the chip, we're going to set the stack pointer to the highest address accessible in the RAM, so that it can then start growing downwards. And we do so by defining a new symbol in the linker script. And this symbol will be then accessible from C code as an eStack variable. But it will be defined during the linker stage, and it will be set to origin RAM to the length RAM. So it will be calculated to be the end of RAM. We also have the heap variables here. Those are we're not going to be using the heap in our example, so we don't need that. Then next thing we do is we define sections, and this is here we define how our code will be placed. So the first thing that goes into this place, into sections, is the interrupt vector. See if we can actually find it here.
ISR, Martin.
Yeah, the ISR table.
Yeah, ISR. And you wrote IRS.
Oh, okay.
Thank you.
Yeah, good. And we set the alignment to be word aligned. So the start of the section align 4. And then we specify which section of the ELF file we're going to place here. So it's going to be ISR vector section. And then we also set alignment here to 4, and we're done with that. And the ISR vector is going to actually be defined inside an assembly file, an assembler file, which will place, let's see, which will be defined like this. So we will actually call this. So if I would have written IRS vector there, then it would still work as long as I have the section defined as the same name here. So this is an assembler file, and when we write like .section, it will actually put this stuff into the ELF file, which is the binary that is produced by the linker, and the section in that file will be called ISR vector or IRS vector, whatever you call it. But in order to tell the linker how to place this section, we have to define it like this in the linker script. So we define this in code, and then anything that is placed in that section in code will go in this section in the final image, right? And then we have our program code. Inside there, we have like a bunch of sections besides text. We can actually just try to keep it simple in the beginning. And just do like this, line 4. And then we just include anything that goes into the text section, and also anything that is a text section dot something. So when we compile, for example, with function sections, compiler option, the functions will be actually placed into different sections, like into subsections of text section. And then they can be, the functions that are not used can be discarded easily when you do it that way. But that's a topic for compiler options. You don't really need to know that this time. And we also have Init and Fini are two sections that are produced by GCC compiler. So there is an option in GCC which allows you to define constructors. So you can actually have an attribute constructor on your function. So you can have a function, a global function, with an attribute constructor. And that attribute basically tells GCC that this function should run when your application starts. It's going to run automatically. But nothing happens automatically when you're working directly on the hardware. So you have to actually tell the linker that you want to include those constructors into your image. And then inside your startup code, you actually have to call them before you call main in order for them to even run. But this functionality of GCC is available through this Init and Fini sections that you can also keep inside the text. Now, next important thing here is that we place this into Flash. Let me just check also if I did that with the previous one. Yeah. So we tell the linker here that this the contents of these sections is going into Flash. Then we have a bunch of other sections, and we'll basically just extend our script as we go. But some of the important stuff is data and BSS. So I'll just copy paste the data section and the BSS section. And here's an interesting directive. So the data section in the executable contains initialized data. So how does that actually work when you compile your program? Basically, somewhere you have to store the initializers for this data. And so it has to go into Flash, but at runtime, you're going to be modifying those variables. So you can't have them in Flash when you're running your application. So the variables themselves, when they are accessed by code, they have to be in RAM, but they have to be placed into Flash when they are being included in the binary. And we achieve that by telling the linker that this is a section that goes into RAM, that is designed to be accessed from RAM, but we're placing it at Flash. So we're going to be placing this into Flash, and we're going to also define two new symbols. S data and E data, which will tell us where it starts and where it ends. So these two symbols allow us then to copy this initializing data, the initializers, from flash into RAM.
Martin,
Mm-hmm.
this we define this script, but then compiler does all these things.
So not really. By default, you have all of this done for you. So you have default linker scripts in your IDE. It's going to use default linker scripts when you build your application through an IDE. But the toolchain expects to have a linker script for your chip. So when you add support for a new chip, let's say nobody has added support for your chip. You're working for a manufacturer, and you're tasked with adding support to whatever IDE, adding support for a new chip. Well, then you have to write the linker scripts. You have to work through the whole script and define exactly where things go for that particular chip. But when you build with an IDE for when you pick your chip in the IDE, then you have already all the compiler options and all the linker scripts or the main linker script that's going to be used for that chip. You can also define things. You can also include other linker scripts into your script. So you can define the basic structure in one script, and then you can define more precisely like what goes where in a particular script for a particular chip, right? Or you can define the size of the memory in a subfile that you then include into your main file, right? So you can kind of like linker script support inclusion, but all of this is provided to you by either the manufacturer or whoever is maintaining the IDE. But here is the thing, right? So if you're using external SRAM, let's say your project involves a memory mapped device, like an external SRAM, and you want to place variables there. Then you need to go into the linker script and actually configure it, because otherwise your processor will not know how to make things work, right?
Okay, yeah, I think that's the point. So then we have to create one section for external RAM, and then we have to create this start and like end, something like that thing address, and where to store it.
Yeah, you can define external RAM here, like SDRAM, for example.
Okay.
And this is how it's defined on the discovery board. So the discovery board has a SRAM, and they use this this definition to define it. So it starts at D010 0000, and it has it's a 4 megabyte memory.
At the end, processor wants to know where this variable located on which memory address.
So here's the important thing, right? So this is not really for the processor; it's more for the binary. So you're telling the compiler. So when let's say you have a function in your code that accesses some variable. Let's go just to make it, to illustrate this a bit better. So if we go into main and let's say we define we're gonna do something we shouldn't do, but we'll define a global variable and we will set it to like if we define it as int var, then this will go into BSS.
Uninitialized, yeah.
Yeah. If we set this to 1 to 3, this will go into data, and the value 1 to 3 will go into flash. So it will stored in flash somewhere. And so, what you're telling the compiler is basically when you do this, when you do an assignment or you read this variable, what address should it read it from? So you can't really achieve that. Like let's say you want to use this external SRAM and you want to store data there. Well, sure, like you can define an array. Like maybe you will do something like Uint32 SRAM, and then you will set it to like D010 whatever. Like it's a pointer, right? So you set it to an address, and then sure you can like access the SRAM with a like an array, whatever, right? But this is very inefficient. Like, you don't want to access it this way. You want to simply define a variable where you place it in a section. So you would have an attribute section. Let me just make sure that I get this right syntax-wise. So you would have an attribute section SRAM. And then in your linker script, this will go into the SRAM. So in your linker script, you can then define that this will be placed in a particular section in the linker script, in the binary. So let's see. So here is just using that for heap. But basically, so when you do it this way, you tell the compile, or you tell the linker how to link those references. So the linker has a reference to a variable, and it looks up the address based on the linker script. So that then you can access this variable exactly like you would access a normal variable, but it's placed into some different address space, which can point to an external memory, right? So if you have an FMC and you configure it to map the external memory into the memory space of the processor, then you can access that memory like normal variables in your code, and the accesses will actually go through the FMC and then get the data from the external memory. So it's really simple. Like, you don't need to add any glue code or any kind of like software way of accessing that data.
Yeah, to linking all this thing and creating binary. What is FMC? I don't know what you say.
It's a flexible memory controller.
It's a flexible memory.
So it's available on the higher end STM32 chips. We can look at FMC.
Oh, so linker does this linking of all memory thing.
Flexible static memory controller, FSMC. So FSMC is able to interface with synchronous and asynchronous memories and 16-bit PC memory cards. Its main purpose is to translate the AHB transactions into appropriate external device protocol, meet the access timing requirements of the external devices. So you can connect SRAM, you can connect dynamic memory, you can connect anything that. So for example, if you're starting your education, you would typically maybe start with some simple processor like the 8051 or something. And then you have your address bus and data bus, and you're accessing sort of everything through the addressing of the address bus. And this is kind of the same way, this works the same way here, but except that this is a specific peripheral that is designed to implement that functionality in a more advanced way. But you can then sort of have external devices that are memory mapped. So you will have your data bus and you will have your address lines, and then somewhere, so then you can map this device into your address space of the processor and access it like normal memory. So it's a very powerful way of accessing external memory. It supports SRAM, NOR flash, PSRAM, and it has a whole bunch of different settings. And so to use, to place variables there, you need to tell the linker that you want them there, so that all addresses and references in your software will be linked to that address in the external SRAM.
So Martin, one question I have, like, for example, as you said, we have to link the external memory into the R code. So, but when it comes to the size, why? Because like here we are segregating the memory into different sections. So when it comes to the size, like as well as the pointer which we are going to give for the external RAM, external RAM. So how do you, how do you integrate that into our code? For example, here, if you started, the memory address is like 0x000 and 0x 2 lakh, something like that. So is it the continue way, like, or do we need to give again the start and the end of, I mean, end numbers for the external memory too?
How do you mean the end numbers?
I mean to say the memory size which is there. So do we need to?
Yeah, you
What to
specify
say?
that too. So you specify that too, and the main reason you do that is to make sure that the linker can check that all of your data fits into that memory.
Mm-hmm.
So you specify it
Okay.
as the length here at the end.
Okay.
Yeah, otherwise the code we generated maybe doesn't fit into that RAM section, and then we get overflow by. Yeah.
Yeah, exactly. And so one of the usages of linker scripts is that you can set your main memory to a much lower amount, just to make sure that your code fits into a certain size of memory, right? So it won't compile if your code and data does not fit into the sections.
Yeah. Gives this error. Yeah, I faced this issue.
So is it is it our wish, or is it any specific reason that we are going to fix in particular memory?
If you have, let's say it depends what you're using the external SRAM for, but let's say you have a you want to place like some large variables there.
Okay.
Maybe you want to place a buffer there
Okay.
for your screen, for your display. Let's say you put your frame buffer into the external SRAM.
Okay.
In order to avoid messing with addresses, you simply define that variable goes into section SDRAM, and then you let the linker decide exactly what addresses it's going to be placed at.
Okay. So we have
so
to
you don't
provide.
have to like, yeah, go on.
Yeah, we have to provide enough amount of memory so that even if something went wrong, or even if something goes high, it will be in limit.
I'm not sure how you mean. So you provide as much, like when you define this, you know already how much memory you have on your board.
Okay.
Martin,
Yeah.
can you, so now in SDRAM, I have to define one array, suppose 1000 bytes. I will do it in external memory, and then if I have to use this thing, I think you explained it, but I didn't understand. In a normal way, like the array size I have taken, or use this array as a pointer, and I can put value into it. How do we use then? So linker does this thing, and how do you use that variable which is stored in SDRAM in our main function or any function?
Just like a normal variable.
Normal variable. Huh? So
Yeah.
then we can access only using pointer. Directly, can we access that thing or not?
Yeah, you access it directly. So when you define it to be in, like normally you would even like do something like this.
So this is what you did, this attribute you write. We have to write that thing. So we have to specify in main function that this variable is defined in SDRAM. So that you mentioned attribute SDRAM. That is the way of telling the compiler that this thing is stored in SDRAM.
This is the way of telling the linker that this variable should be stored in SDRAM section. The compiler, what the compiler will generate in the let's just go through the compilation process. So your compiler will compile your C files into object files.
Yeah.
In your object files, variables become references, like virtual labels. They become labels, right?
Mm-hmm.
And then when your linker is linking the final program, those labels are then translated into actual addresses based on the linker script.
Mm-hmm.
And so if you specify something like an attribute to place this variable inside a particular section,
Mm-hmm.
then in your linker script, you would include that variable in that section. Like, for example, here we include the ESR vector, we include the text section into the text of the executable, etc., right?
Mm-hmm.
And so it's the linker script that tells the compiler where to place those variables. And we define also, so yeah, and at the end of each definition of a section, we define where it goes.
Yeah, I understand.
So
I
if
mean,
this one goes into Flash, anything that is also placed into Flash will be simply appended at the end of that address space. And so when the linker is linking, it will translate those labels into actual addresses. And so your code will automatically then read from the right addresses. So it kind of like patches everything up once it produces the binary, and then your code can directly read from locations that are in the correct place.
Yeah. So here you did it. I mean, now int -- SDRAM. What is this SDRAM? I mean, why you did it? Why you didn't do just
I
int
basically
var?
defined a macro.
Yeah.
Oh, sorry.
Why this macro means
No. This is wrong. Let's see. Like this. So instead of type def, let's see. So I basically defined a macro that replaces, so SDRAM, then I can use like this. Then I can do like SDRAM var2, right? So I don't have to type that.
Yeah, no, that I understood. But what so this you define initially only dash anyway SDRAM, this dash attribute dash dot SDRAM. This attribute, what is this attribute? I don't know.
Yeah, attribute is a compiler attribute.
A property of one variable of compiler.
No. Let's see. I will show you.
Okay.
If you search for GCC attributes,
GCC attribute. Okay. Research letter.
and you have function attributes and you have variable attributes.
Okay.
So you can see like there's attributes for many different architectures, and there's also common variable attributes. So you can have like alias, you can set alignment, you can do a lot of different things. So for example, you can specify an attribute for almost anything. And so attribute SDRAM is one of the attributes.
Okay. Yeah, I mean, I will search and read more about it. Yeah, thanks.
Yeah.
Yeah, even me too.
Sorry, Martin. Could you actually send this link into chat, because we have more
yeah, we can go through that. Yeah, that is true.
Absolutely.
Thank you.
Oh, that's opening up here.
Hello.
So Jerome posted also a link to explanations. Really good stuff here.
Yeah, please. Yeah, I mean, yeah, on this topic also on linker, if you have any information so that we can read it, that would be.
Yeah, well, that's like if you search for GCC attributes, you will get both function attributes and variable attributes. And this is very useful because you can set things like GCC has attributes for constructors. You can actually have constructors in C, which is useful sometimes.
Okay.
And you can place addresses. You can have functions that where you place the addresses of the functions into a specific section which just contains addresses. And then you can call those functions manually from your startup code, which basically translates into a way of initializing your drivers at startup in the order they're defined in the source code. So you can kind of do things with the binary and set parameters of the variables. You can define how many bytes are used for aligning this variable. Shall it be always like placed into even if it's a 16-bit variable, shall it always take up 4 bytes regardless of architecture? Then you can specify that with an attribute.
Nice info, thanks.
And so once once you have sort of placed your variables, you will then basically through the linker, they will be placed into a section in the final ELF file. So we have the data section, we have the BSS section for uninitialized stuff. We actually have two labels here. We can just remove that. And then there is a number of sections there, normal BSS sections, and then common is generated by GCC. If you want to know more about it, it's like, it's some like housekeeping that GCC also puts there. Right, so it's like uninitialized data objects that are not yet allocated.
Mm-hmm.
But all of that goes into BSS. And BSS, since it doesn't have any initial values, it's placed into RAM only, so it doesn't have any references in Flash for any data. So that's a basic linker script. We might need to add more stuff to it, but we'll start with this, so we can move on. Let's make a simple Makefile.
Yeah.
For building our application. So I'll open up the Makefile I have here. We're going to start by just sort of defining our files. We're going to have program name. So we define a few variables so that we can just reuse those variables. So this is a bare application. It's going to have object files, objects bare.o, and then system STM32 F4XX O and startup. And those files we haven't created yet, so we'll create them. These files are provided by your standard peripheral library, normally. So when you build with an IDE, those files are included directly into your build. But we do need to include those files when we do a basic application. Now, next thing is the target flags. This can be, you can find the right flags usually from like documentation of the compiler. So for example, we picked the MCPU. We are compiling for a Cortex M4 core. We are using the thumb instructions. We are setting this to be a little endian system, and we set also FPU to be a hardware FPU, and this is the FPU that's used on this chip. And we also specify that we want to use hard float, so we want to use the FPU, and also thumb interwork. Let's see what that's. It's basically a variation of instruction set. So you get slightly bigger code size, and they're defined here.
Oh.
What happened?
Again.
Again. I think this is some kind of like a feature in Zoom where you can set, when you can like draw on the screen.
Join the screen.
But I'm not sure how to get rid of it. Like, I don't have any controls. I don't have anything like to disable it or something.
Video panel then Finster.
Yeah, even we also don't know. I don't know. It is, I think, as you said, like it is for just drawing something.
Yeah, exactly.
And you already drawn something.
No, it's actually one. It's actually one of the participants that drew something, but it's weird that it's just a black screen. Like, I don't have any controls. I can't really get rid of it. Let me just see here.
Somebody requested for annotate. That's why, see, just like this way. Somebody.
Yeah, but
Sagar Ram, something name is written. Who is it? Sagar.
So now I have done. Earlier I have.
Okay, now you are done.
Just for demo.
Okay. Okay, sir. Okay. Who is then drawing? Then I think he need to come out.
It should be, I mean, actually this control should be with, if it is with Martin, then it would be good. Otherwise, everybody will ask for that.
I think it
Whoever
is
is the host, he can disable it. He can disable
Yeah,
this
I
one.
guess.
Yeah, I have to check how I can disable it. Let's see.
What is this next?
Sagar, do you know how to disable it?
What option got enabled? Can you tell me the option?
Annotate. Option name is annotate.
Annotate. I don't know. Here is something in everything.
When somebody is sharing screen, you can request that.
Yeah, we are back.
Nice.
Let's see.
Sound is something. Hello, Martin. Can you hear us?
Yeah, there we go.
Okay, nice.
So I have the controls when the annotate is not on, but when the annotate is on, the controls disappear. It's really weird.
Yeah, I think you should disable for some extent.
Yeah,
Otherwise, people
I
would
need to
like
check,
to write.
check Zoom options. I think there is like options for the meeting to disable annotate and disable maybe a few other things. But let's see. So we have the interwork. So the interwork is basically like to generate code that supports calling between the ARM and thumb instruction sets. So I suppose this would be useful in a system where you maybe have libraries that are in different instruction sets, and then you can sort of be able to interwork between them. So we don't actually need that. We can just do like that. I don't think we need that. We can leave it there for now. But then, so this will be our target flags. We specify that we're compiling like a bare metal application. There is no system on it. And then we also specify our C flags. So this will be our compilation flags. And we want to have debugging information. So we specify G. We want to have all warnings enabled. We want to have extra warnings enabled. We want to have, we want to make sure that all warnings are errors. And we want to specify our target flags here. So we're going to be using our C flags as the main compilation flags. But we're also going to be using target flags in our linker flags. So we want to kind of make sure that we have them separate. We're going to specify CMSys include directory. I haven't created it yet. I can create it here. So CMSys, no, it's supposed to be a directory. So
Martin,
we'll place the ARM CMSys files there. We also then define the, this definition is used for the STM32 default files. Let's see. So this is used to pick the chip in the STM32 system file, which comes from the STM32 library. It actually uses a bunch of defines here to pick the controller that you're using. So we can keep that there for now, and the HEC value is also used by the startup code. Then we have our LD flags, and it is in the linker flags that we specify our linker script. So we want to compile our, we want to produce our object files from our C files using the ARM non ERB GCC, and we pass the C flags now to this compilation command. So now it becomes apparent why I have defined C flags here. So basically, GCC will be called with these C flags, and we specify we want to compile, and we specify the output file, and we specify the input file. So the output file is the O file, and the input file is C file. So this is a generic rule for all the C files, for converting C files into O files. Now we have another generic rule for converting assembler files into object files. So it's going to be ARM, non, ERB, GCC as well. So we can use GCC as quite a, like a main, so GCC will actually call the assembler, but it's the same command, like when you can use the same command. It will automatically see that you try to assemble an assembly file, and it will just use the assembler to create an object file from it. So we have a C flags, C, O, and same thing basically there. Now we want to define a rule for our program.
Martin, we don't convert .h file into object file?
No.
No.
The H file is just for your code to make sure that the compiler knows what functions you're trying to call. So if you're calling, let's say you're calling printf from your application, and when you're compiling that C file, the compiler doesn't know what printf definition looks like because maybe it hasn't compiled printf yet. But through the header file, you tell the compiler that this function takes a format argument, and then it takes a variable number of arguments after it. And so it can generate code for that definition of for that declaration of the function. So header files basically give the compiler the template for function calls to a particular function. And then you define the function in a different C file. Yeah. And then the linker will link those references together so that the call to printf will be will result into actually calling a printf function, which is actually defined in a different C file.
Yeah, understood. Yeah.
So then we have a rule for producing our program, which I've defined program up here. So program is called bear, and objects are the object files. So when I define it like this, what this means is that the make command will look at the object files, and if any of them have updated, then it will relink the program. But in turn, because we have another rule here for which is a generic match rule for object files, it will also then check that the S file is updated or not, and it will recompile it. So this the way of defining like targets in make files basically makes sure that if anything changes, then your application is recompiled. And that's what make takes care of. So this is to produce program from object files. So here we can also use GCC, but we're actually linking the program in this step.
Sorry, Martin, I have a question.
Yeah.
Because we have ARM non-IAB GCC twice, one is for .c, second one is for .s. Yes.
Yes.
And we have C flags -c-o in both of this. It should be like this, or it should be
that is correct.
Okay.
So this is the first rule is for C files. The second rule is for S files, which are assembler files. And the reason I have an assembler file is because we're going to have startup code written in assembler in order to initialize the BSS section. So we don't want to use any variables there. The first thing we do, so we have a little bit of code in assembler that will initialize the BSS section to zeros, and will also copy the data section from flash into RAM.
Yes, I know, but what means this C flags? We have C and O in one line, and in second line we also have C and O. Okay, so C flags is basically this variable here. Yeah. So this will translate into the flags that I've specified, and I want to include. So G means I want to include debugging information. Then I have I want to make sure that compiler generates all warnings. I want to make sure that it also generates extra warnings.
and I want to make sure that it treats all warnings as errors, so that it doesn't compile the file if there are warnings. And then I also add another variable here. So when I use this syntax with a $sign parenthesis, it means that I want to take the value of this variable and paste it here, basically. So
Okay.
So C flags gets also extended with these flags. And then here it becomes one long command line for compiling. And so -C means compile. So it's not going to link, it's just going to compile. And -O means that this would be the output file, which is specified as $@ which is going to translate to the file that matched this rule here. And then this would be the output file, this so -O output file, and then $, so less than, that means sort of, it's like an arrow, and it means that this is the input file, which would be the C file.
Okay, thank you.
Can I ask the question too?
Yeah.
I need to know, don't we have to write a rule to generate the pre-processed files in this .i files?
Which files?
The pre-processed files that include the source files and its function definitions in the header files, the ones with .i as the extension.
You don't need to generate pre-processed files. Do you mean like you're on preprocessor and just have pre-processed files? Like you would need to do that though. Like you can add more rules in order to generate lists of header files that are in use, so that you can recompile if any header file changes. But you don't need to have an extra rule for those intermediate steps. Like I can have a rule to generate an assembler file out of C file, and then from the assembler file I will generate the object file. But I don't really need to do that. GCC takes care of that in the background. Like if I just specify, so it uses the file extension to determine what it needs to do. So if I have a C file and I want an O file, then it will just create the assembly in its own, like maybe temporary file, and then it will just create the object file directly and output that into the object file, whatever result that is, whatever is the result of the compilation.
Okay, thanks.
Sorry, one question, Fixer. What is called this programming then? We do this thing.
Oh, this is just a text editor. So somebody said that they wanted to have a bigger text, so I started Vim instead. I could just zoom in on the full window.
No, that's okay. But this is scripting. But any name to this generating Makefile or something? It's called some programming. It's not like .c or .h files. What is called this thing?
Yeah, he said it is for creation of the Makefile. Like how do we write Makefile generally? So he just added them.
Oh, you just use any text editor you want.
Okay.
Yeah.
Okay. Thanks.
So it doesn't really matter. But if you use an editor like the Vim editor on Linux, then you have syntax highlighting for all languages. Like there's syntax highlighting for almost like anything I can think of. There is basically a syntax highlighter for it.
One question, Martin, here. Like if we see this C flags or LD flags, and above that there is target flags. So these are the architecture specific, or these are general for the ARM processor?
The target flags are specific for this chip.
Okay.
So, or specific for this family, I would say. So we're using Cortex M4, and it has it has a hardware floating point processor inside it, and then different versions of the F4, the F4 chip. They have different peripherals, but they're all using they all can run the same code.
Okay.
So these things would be different for an M3 or like Cortex M0. Then you would specify Cortex M0 here.
Okay.
And those flags are you can see those flags if you have your IDE and then you compile your program and you can see the command line that's being invoked. You will see the flags that they're being passed to the compiler. So if you want to then sort of have your own Makefile, you can just copy them from the flags that IDE is using and adjust that to your needs, basically.
Okay.
So now we have done. Any other questions, by the way?
No, from me not.
Yeah, one more. Like in C flag section also, that is related to the family of the process, or it is because ICMC, it is related to ARM mostly.
So ICMCs means that this is an include path.
Yeah.
So let's just remove that for now. We remove this and we remove this. So we can add that later as we write the code, right? It will be easier. Then LD flags, I specify WL means that I'm passing a linker flag. And then behind the comma, I specify the -T means that I'm specifying a linker script. And this is passed to the linker. So here, because we're creating a binary, GCC will actually automatically invoke the linker.
Okay.
So we then need a few commands to flash our firmware. And I will be using basically OpenOCD to flash it. And I will also add a target for debugging. And this is just to, so when you specify this in a Makefile, it means that Make will not treat this as files. So by default, Make treats every target as a file. So this means it will not check the modification date. So
okay, if you write OpenOCD, it won't consider it as a file.
No. So this dot phony here.
Okay.
Dot phony means it's a make directive, which means, let's see, which means that these targets, flash, debug, and clean, even if they exist as files, like let's say I put this flash as a file in my directory, right? So if I do like this, flash. So now it's a file. So now it will look at the modification date, and modification date can actually mess up the build process. If it can choose not to actually build this, not to actually execute this, if it's a file. So I don't want it to actually check for the existence of this target, because this is just going to be a make target. So that's going to execute OpenOCD. So I specify this as a phony directive, which means that these are not treated as files. It's just like a little detail in Make. So what is the purpose of phony in Makefile? Let's see what they say here. So yeah, by default, Makefile targets are file targets. They're used to build files from other files. Make assumes its target is a file, and this makes writing Make files relatively easy, right? So foo is a file which is created from bar. However, sometimes you want your Makefile to run commands that do not represent physical files, which is exactly what we're doing here. Because we're going to be calling this as a target that we want to build. And clean, for example, is one example of that. So you specify it as a phony, so it's not treated as a file. And so Flash will basically use OpenOCD. It will specify the configuration script for the discovery board, which we are building for here. And it will specify also the command that we're going to be running. So to flash a new firmware with OpenOCD, all we have to do is basically tell OpenOCD to program, and then we have our elf file here. So this would be the binary that's been created, which is program, which we set here up here as a variable. So I set it at the top here as bare. So that will basically flash that file and verify it, and then reset the chip and exit. And debug means that we're going to start GDB, and we're going to connect to the target using target remote localhost. And the reason it's like localhost 4242 is because ST comes with a utility like ST tools for STM32. They come with a utility called stutil. And when you run that, it actually starts a GDB server at localhost 4242. So that's why I use that from the GDB here to then connect to the target. So yeah, this is like when you have this minimal setup, you basically compile a program and then you can debug it, and you have everything, and you kind of understand how everything fits together from these few files. So it's a really good starting point if you really want to understand how things are built and how they're linked, how the binary is generated, and like how a bigger project is built kind of becomes apparent when you understand this process. So we also have a the clean target, which just removes the object files and remove the executable. So now we have a Makefile. It's probably not going to build it, but we could try. Let's see. Yeah, it's not going to build it because we have missing files. So if we just type make here, we're going to have no rule to make bare O. Which is, of course, apparent because our file is called main, not bare. So we're going to just replace this with main. So now we should be able to build the. Now main compiles, and now we need to also create those startup files. So I'm just going to remove this attributes because we're not actually using this for our application. So we have our main file. And now we need to actually create this the first bytes of this executable. So we're gonna create our startup file, and this will be the first section that will contain. So in our linker script, if we go back to our linker script, the first thing that we have in our Flash. So because this is the first section here and it's placed in Flash, this is actually going to be the first section in Flash at this address of 0x0800 here. So 0x0800 000. This is the Flash memory in our datasheet. And because we're placing it first in that like this is the first section that goes into Flash, it's going to be the first thing that is placed in the Flash. And what do we need to place the first thing we do in the Flash? Well, it's our stack pointer and it's our instruction, the instruction counter that is going to contain the address of the first instruction that the processor will run. And the way we achieve this is by writing a small assembler file that we'll call startup.s. And in this file, we will define our section for this ESR vectors. So here. So the first bytes are basically just telling the assembler the CPU, the FPU we're using thumb instructions, so we can just, those are just parameters for the assembler. We also have a bunch of variables here, which are defined. So this is the variables we've defined in our linker script. So we have word s data, word s e data, start of data, end of data. We have word SPSS and word S or EBSS. And this is basically like defining an int S data, for example. It becomes like a label for an address, which will be filled in by the linker during the linking stage based on the information in the linker script. And then we need to define our section for the ISR vector. And we also will we'll create a global variable here. So, and now we can actually place things into this section in the assembly. So we will just place the word for eStack, and we'll place the word for the reset handler. So this can be an arbitrary name, actually, because we're just naming a variable, right? And so this will be the first byte in Flash here. And processor will actually load them automatically. So it's part of the startup process. So they'll load two registers, stack pointer and instruction pointer, and that will start executing the program. Now we also have a bunch of other things here, which is all the interrupt handlers. So this contains references to all of the interrupt handlers, which you define this in your code, right? When you're programming STM32, you will write, like, if you want to have an RQ handler for UART7, you will define a function in your C code, which is called UART7 RQ handler. And the way these things are linked into the binary is basically through this table here. So we will start with just the basics, and then we can extend this. Then we have our section for the reset handler, which is going to be placed in text. It's going to be called text.resetHandler. And this is a weak symbol, which means that you can actually have a different definition of it elsewhere in your code, which will replace it. And so this will be the entry point of our application. So reset handler is the first thing that will run when the application starts. So the first thing we do is we're going to copy the initialization values for data. And we have the SE data. Let me just check if we have that in our LD script. Right, so we need to add this label here.
Martin?
Yeah?
Someone mentioned that a lot of people are waiting in a room or
really?
something like this.
Let me check. Oh, there are a few, yeah. I'm gonna admit all. Cool, thanks. So we need to copy this as well. SE data, this would be start of the initialization data. It's going to be the load address of the data section, which will point into Flash. So we'll copy this into our file here. We'll add a new variable.
Okay. So startup file is written in assembly, huh?
Yes. Yes, and the reason for that is because you don't want to have any kind of variables accidentally accessed, because you still don't have the initialization values. So you want to have like really rigorous control over what is running in this very beginning. So the first thing we do then is copy over this initialization data. So we will move into R1, we will move value of 0. And then we branch into loop copy. And then we have a loop, then we have copy init here first, but then we have loop copy. And loop copy will basically, oh, no, not again. Let's see. The funny thing is that the controls disappear when that happens.
Actually, somebody has shared one link how we can disable it.
Okay.
So, yeah, I think you can do that.
I'll check it out.
Yeah. First thing is we have to get control back, then we can do anything. Who is that person? Every time he would like to write.
I don't know.
No, it's different people every time, actually. It's not the same person. It's probably people that are watching through like a tablet.
Yeah, sometimes it might happen, like unknowingly.
All right, there we go. So yeah, so this is basically just a small loop that copies the initialization data. And it's written in ARM assembly. Basically, we will load into R0 the address of the start of data, and then into R3 the address of the end of data in Flash. And then we'll increment, then we'll add R0 and R1 and place the result in R2. Anyway, this is basically a for loop. So this is basically the same as like writing like this. So for int c equals s data, c less than e data, c++, and then copy into BSS in RAM, or no, not data in RAM, C equals data in Flash C. So this is basically what it does, but it's written in ARM assembly. Load, store, and increment. compare R2 and R3. So this is basically check if C is less than size of, or less than E data. And then branch to copy init. And then when we're done with that, we basically fill the BSS with zeros. And this loads the ending address of BSS into R3, and then loops until basically we until R2 is equal R3. So because we are branching here to clear BSS, then when we store this, we'll actually, so this stores R3 into the location pointed by R2 and increments the R2, and then it continues here. So it will actually, again, copy into R3 the EBSS, and then compare, and then branch if it's still not equal to R3. So this is also like a for loop. And then once we're done with that, then we call our first C function, which is system init. So now we can go into C, and now we can actually start calling STM32, like right into STM32 registers. And when that is done, we then call our main. And I think BXLR means basically just loop forever. Oh, it's actually like a return. So, but there's nothing to return to. So it's never going to return anywhere. And then we set the size for this reset handler, which is defined as the size of the section. So this is the startup code. This is the stuff that is executed before you actually call main. So if we compile this, we'll actually also add our system. So let's see, system C. And in this file, in the Makefile, I will replace this with system and this with startup. So if we compile this, we'll get undefined reference. Let's see. Syntax error at line 5. That is so weird. What if I just copy this line?
I think somewhere we.
Oh, I know what's wrong. I know what's wrong. The spaces. Look at this. The spaces.
Huh? Oh, okay. Yes.
It's so sensitive for every single little detail. Wow.
Oh.
That's the problem. So now it's working. Okay. So we have, we actually, because we're including the floating point support, we have actually, we need to have this BSS end, which is used by GCC code. So this comes from like libgcc, and it's basic, like it's support for the floating point processor, like instructions provided by GCC. So we'll just add that so we can keep GCC happy. And it's BSS start here. Let's see, SBSS. So we'll add the start, and we'll add this symbol for the end, which will link with GCC code, which actually comes from GCC. When GCC is compiled, it gets some code that that it can use to link ARM executables to add floating point support to them. So undefined reference to system init. Well, let's go and create our system init. So we have our system C here. We will just create an int system init. It doesn't take any arguments, and it returns, or it's actually a void. Let's make this a void. And then let's try to compile. So now we have compiled it. Let's see what happens if we run it. Let me check. Right. So now we got into main finally. I was missing an increment.
Okay, increment of instruction.
Yeah, I was missing an instruction here. Add s. So in this loop, an assembler instruction.
Okay.
And so this, let's see. Let's look at what is actual definition of this. So add s arm instruction.
So Martin, all these, what do you say, the initialization code instructions are specifically related to ARM?
This is ARM assembly. So this is actually thumb instructions. So you're going to be using like very similar instruction on all ARM processors.
Okay.
But they're going to be different for x86, for example.
Okay.
But the principle is kind of the same, and this is why you don't want to write this stuff yourself. So this is like, it's a good example, but it's really
Yeah.
easy to mess something up, and it's like your life is easy when you're working like at higher level with an RTOS and your application.
Yeah, that is true.
But when you get to this low level, so add s is basically. So the S is specified, this instructions update the flags. And add is basically RD. So RD is the destination register. RN is the register holding the first operand. And this is a flexible second operand. Add without carry. So this is basically R0 plus R1 and place it into R2. And so, and then we compare R2 to R3. Yeah. And if we don't have this, then our R2, let's see if we're using R2 anywhere. No, we're not using R2. Yeah, but basically this loop would not work without this instruction. So that's it. This is like the basics, the basic starting code. Like this is the minimum. What I haven't talked about today, which I didn't have time to talk about today, is the actual sort of system startup code, which sets the clocks. So the STM32 starts with. So actually, we can take like. So if we would have gotten here sooner, then I would actually bring up the clock registers and sort of the PLL. So we are not running at maximum speed when we just start up. We're running an internal oscillator, and then we need to configure the external oscillator in order to run at 168 megahertz. And to do that, we need to set all the RCC registers, which is done here. Yeah, do you want me to go through that?
We can go tomorrow if you're okay.
Yeah, all right.
Yeah. So where is Patrick? So
Patrick is there.
Yeah. So
Patrick,
I mean,
Patrick is from Poland.
Yeah, he told me. He told me. We had some discussion earlier.
Cool.
So Martin, so this startup code is, I mean, how, how required is this? Like, is it good to learn this? Like, I mean, how to write startup code?
Well, it's good to learn it if you're gonna add support like for a new chip, but in a typical setting, you don't really need to know it. But people have been asking me like, how do I set up minimal STM32 project? And minimal STM32 project is basically having the startup code from ST library. So typically you just reuse the startup code from ST libraries. So you take the startup file, you take the system file, and then you just add your own code. And this is the minimal project for an STM32. It has all this stuff is like in the standard peripheral library. So like setting up a really minimal project is basically just including that code and compiling it. Yeah. So I think one of the ways to like, I could have probably made it a little bit more fun. I think it took a
it's
long
okay.
time.
It's okay. It is like actually it is first session, right? Like, so you will come to know many things, and again next session it will be going to fun, as you said.
Yeah. Sorry, next session. I didn't quite get the last.
No, what I am saying is today is the first discussion. Like, I mean, for me it is exact. I mean, and for so many people.
Exactly.
So, and moreover, you stuck with something like you're debugging. So that's why there are so many things which you would like to discuss, but it took some more time. So we can discuss them after some time. It's okay. But yeah, it is good. Like today, what we have gone through is like we had gone through how to write the startup code, as well as how to write the make file, as well as what are the things are there in linker file, and how we are integrating, or how we are bringing the external RAM into the existed code, and we have seen a couple of things.
Right.
Yeah, I mean,
what do you want me to bring up next time?
Actually, I don't know. There is one thing every time which runs in my mind, Martin. Like people do say, like writing application code is good, but understanding low-level drivers is really important, because that is what is going to drive total system. So we can discuss like low-level drivers, like how do we write drivers for example, if you have a any motor, like an induction motor or stepper motor, so how do we write, how do we control the torque, and something like that. I mean, I really don't know how to write the drivers, like because writing drivers is two things. One is to understand the existing hardware, and the second thing is we have to write the code according to that hardware and with the components that are available in our ARM processor. So yeah, so everything combinedly people write. So I feel it is really complex, and I just know how people write, but I never gone through that. Yeah.
Yeah, I think one of the so I think for the next time we could actually go into the Zephyr RTOS.
Okay.
And, we will do. We will also use the discovery board, because a lot of people can get that board, and it's easy to play with it. But kind of do the device driver stuff at a little bit higher level.
Yeah.
But I've been thinking about that, and what is not 100% clear for me is exactly at what level to start it, sort of where to get in and where to start, so that everybody is with me. So maybe the first thing is not going to be a motor controller, because that would use a lot of different peripherals.
Yeah, that is true.
And that is
hello,
more
one.
of an application code, because it's it isn't really related to device drivers because you're actually reading stuff from the devices, so using the device drivers, and then you have your application that calculates the torques and things like that.
Yeah.
So,
So
do you have any suggestions, like on what level you want to start? What exactly do you want to know more about in the device driver?
For me, actually, what I feel is like whatever the topics that you covered today. So most of the things are I haven't gone through them earlier days. Like I didn't get a chance to know about all this. Like this is the first time I'm seeing few things. Like I never saw like writing the startup code, which will start earlier to the main, and understanding Makefile that I have gone through, but this linker section and everything I haven't gone through. So this is pretty good start, I feel. And if you have a plan to build upon something on this, then you can go ahead. Like that will be really good.
Okay, cool. That gives me some good ideas.
Yeah.
So, thanks.
And Patrick, you were asking something.
According to what we may do on this webinar is example. For example, if this example like getting data by SPI from some sensor or some memory will take more than 1 hour, we may actually divide this on couple of sessions.
Yeah.
Because actually, if we correctly understand one example, we may actually take this to another one.
Yes.
Actually,
so,
we need some sort of the way of looking.
Yeah, so that is what even I was also talking with Martin. So he already had good start. So if we build something on this, so that will be the example as well as reference for further projects.
Yeah.
So
right.
Yeah,
that actually makes sense. So we have a basic application and then build on it.
Yeah.
That would be a good thing. And another angle that I was thinking of is actually, have you seen? So there are a few projects. There are notably 2 projects. There is one called Virtual Boy, which is a Game Boy emulator, which is actually a processor written in Verilog, and that processor can run C code. So you can actually compile a Verilog program into a simulation, and then you simulate on a processor that kind of is represented by actual logic of the hardware. Like if you were to put that into an FPGA, you would actually have a processor that works like a Game Boy, right? So that is an interesting system, which is very simple, and it runs basic C. It's kind of like a very basic system. But we actually then have both the hardware files, and we have a compiler, and we can write C code for it, and we can run it on the computer without actually needing to have any hardware. So it's kind of an interesting angle on it to actually learn microprocessors. But the main problem is that it's not very useful in the real world. It's more useful as a theoretical experimentation platform. For just understanding sort of how a chip is actually made. So what do you think of that?
Yeah, that is good idea. Yeah, as you said, like we can do that.
I'll send a link here. So I'll send a link in the chat.
And one request, Martin. So do you have any kind of material or any kind of thing like that how we start, how we write this linker programs and everything. Because I got some idea right now, so I would like to do hands-on. So how should I start?
Then you can go to let's see, GCC LD script book file type.
Okay.
Let's see what we can find. There is all documentation for the linker, but you kind of need to understand what to search for, right? So introduction to the GNU compiler and linker. We could actually find some things here.
Yeah.
Can you see my screen?
Yeah,
Yes.
I can see.
So there is quite a lot of info here. Sections command. Yeah, this explains a lot of the stuff that I have explained to you today. But it's not really related to STM32, but it kind of explains to you a lot of details. This is actually a good file. I'll post it here.
Okay, that is completely related to compilation. I mean, compilation.
That's related to the linker.
Okay, that's
to the linker script.
Okay.
Okay, what else?
So yeah, along with that, and one more thing, like I would like to ask. So yeah, we do write a linker program, as you said. So okay, for example, I had connected one more extra RAM. Okay, from how we did in this project. So I mean that is pretty same, right? So how we manage the memory and everything, that is pretty same, right?
The same in what way?
Same in what is allocating memory for data sections and allocating memory for code section. In that way, I'm asking.
Okay, so you're not actually allocating any memory, but rather you're pointing, you're specifying the memory that you have, so that the compiler can place variables there. So the compiler will just give your code an address, and that address is going to be placed somewhere in memory. And the linker script tells the compiler the architecture of the memory, where we can place things, because we don't have any memory management or like we don't have any virtual memory on the chip. So everything is kind of in the same space, and we have to specify that at compilation time where things are placed, so that all the offsets are correct. So yeah, that's you're not actually allocating memory. You're specifying your layout of your program.
Okay, so it is something like we are pointing. I mean, okay, something like that.
Well, it's kind of like let's see, I can do like this. I will just see if I can find that. There. Let's see. So it's kind of like you have your variables here. You have your like int var. And then this variable is actually an address.
Okay.
And this address is pointing to a section somewhere in the program.
Okay.
And these are the sections, right? So this address points somewhere there. And this address is actually a label that gets translated into this value at linking time. And it's only during linking time that the linker can place things into memory in executable. So it's kind of like in order for this translation to take place, you have to define things in linker script so that the linker knows which values are valid, right? So the linker basically told which values are valid, and so it can choose from which values are valid, and then it places things in those sections.
Okay. So yeah, so what linker will do is like, okay, it will take this as whatever you wrote, 00123. It will wrote, it will become a label, right?
No, variable. So int var will be a label. If it's like yeah, it's basically it will be a label in the object files, and then that label in code will be translated to actual addresses, which will be used to access that data.
Okay.
Yeah.
Yeah, understood.
So it's the same thing for functions. Like when they're compiled into actual machine code, but then certain things need to be patched up when you create the actual program, the application, because you don't know all the code that's going to go into the application. So addresses are going to be different for functions when they're actually linked. And so during the linking time, the linker will actually translate and patch those addresses based on the layout of the executable, on the layout of the program. And then that is all stored in the ELF file. The ELF file format is the extendable, let's just double check what it stands for. But it's the Linux executable file format. So what does ELF stand for? That's a good question, right?
Like Legolas.
Exactly. Like, JTAG stands for like joint something group.
Yeah,
I never would have
joint,
thought.
joint testing something.
Yeah.
Action group.
Yeah, exactly. Executable and linkable format. That was simple. So during this linking time, the linker will actually then resolve those references, right? So do you know sometimes when you link and you don't have a function defined anywhere, you will get unresolved reference to, and that it couldn't find the address. So the name of the function is like a label, and then when you link the final executable, that's when you translate that label into actual address based on where the linker is chosen to place that function. And you can kind of see it if you do like if you use the obj dump utility. So arm non erb obj dump, and then s for disassembly, and then we can do like this, and we can do less. So this is the disassembly of the program. So when things are played, like when all the functions, machine code is actually placed into the final executable, then you get this list of functions, and they will have different addresses depending on how you link them. So the labels need to be resolved whenever you call a function. And this takes, all of this is patched up properly during the linking time. And so you can place things into different sections. And if you then define, if those addresses point to some external memory in hardware, then you will be accessing that external memory when you access those addresses. And so, and then those addresses are then used in your application automatically when you access variables if you place them into a particular section. So you don't have to think about particular addresses. You can just use variables as normal. But if you place them in a section and then define that section in a linker script to place it at a certain address, then you can be sure that those variables will be in that address space. So they might actually be placed at an external RAM through hardware support, of course. But that's kind of how the linker script comes in. It basically tells the compiler where the data will be placed in memory.
Yeah. So according to that, it will be placing.
So that's it for today then.
Yeah.
Thanks for being here, and I'll announce the next workshop. So we have a next workshop now, actually tomorrow. We're gonna do KiCad workshop. So tomorrow I'm gonna be just focusing on KiCad.
Yeah.
The next C workshop is going to be on Thursday. Also, the recording is available in Academy if you have a subscription plan. So the recording will be uploaded there, and I will announce also the next workshop through the calendar event. So you'll get an event notification for the next workshop.
Okay. So one question, Martin. So I had gone through one book, I think like last month. So there is like the book name is like what to say, embedded approach of FPGA through embedded C. So they are writing code in C to run on FPGA.
Yeah.
Yeah. So I don't know like how they are doing. Like okay, see, for example, FPGA requires like a VHDL or Verilog. So nowadays they are saying that you can write in your own C and you can run it on FPGA.
Yes, you can do that. And Xilinx FPGA support that. So what they do is you write your code in C, and then you can use pragma statements to tell the compiler that you want to accelerate certain loops. So it's not the same as actually writing a code in the hardware description language. And the reason for that is because you're not actually, you can only accelerate like simpler things and loops that do the same thing many times. But normal like C code is sequential. So if you just write arbitrary C code, it's going to actually execute sequentially. So you kind of lose the whole benefit of FPGA. But it makes things simpler. And actually, right before this workshop, I was interviewing a guy from Xilinx, and I'm going to be uploading that interview. It's actually a really good interview. Where we talked about precisely this subject of how they provide the tools for you to be able to write code in C and then use the acceleration on the chip. So they have actually chips that have an ARM processor and a and FPGA core on the same chip.
Okay.
And that allows you to have custom logic inside the same processor. So you can actually upload a soft core in there and use it alongside of your Linux processor. And they share memory, they share all the resources, and it's very like you really can do a lot of things in that approach because you are in the same chip. You have fast access to all the memory, all the peripherals, and everything on the chip that Linux has access to.
Yeah.
So that's really cool. And I was really happy with that interview. I'm going to be uploading it as soon as I'm done here. So it's going to come up on my YouTube channel. And you can watch it there later today.
Yeah.
And if you're subscribed to notifications on the website, you should also get a notification about anything new I publish on the website. So it will come up there as well.
Okay. So the website is like the Swedish embedded, right?
Yeah, swedishembedded.com.
Yeah, yeah. So you're from Sweden?
Yeah.
Okay, I think you might be living in Stockholm.
Exactly.
Great.
What city are you from?
I'm from Hyderabad, India.
Sorry, what was that?
India.
But which city?
Hyderabad.
Hyderabad. Okay.
Yeah. There are two Hyderabad's there. One is in Pakistan and one is in India.
How do you spell it? Like
Hyderabad. Yeah. Hyderabad. Yeah. Perfect.
Oh, okay. India is such a big country.
Yeah. So yeah, this one. Yeah, here only. So yeah, that one. Perfect.
Yeah.
Like in the middle, or not?
I lost it. It disappeared.
Okay, just type Hyderabad. That's it.
Yeah. There.
Yeah. And one more is in Sindh, Pakistan. In Sindh, there is one more Hyderabad.
Oh, very close to India.
All right. Cool. See you later then, guys.
Yeah, sure.
Thank you.
Bye-bye.
Bye.
Yeah, have a good day. Have a good day, Martin. Have a good day, Patrick.
Thank you
Thank
very
you.
much.
You too.
All right.
One more person also there. Have a good day, Chayan.
Yeah.
Yeah. Bye.
Bye bye.